All right, so let's talk about this. This degree sign, we talked about it last time. That means standard conditions, and thermodynamic standard conditions mean that the temperature is 25 degrees Celsius, the partial pressure of all gases is 1 atmosphere, and the concentration of all aqueous solutions is 1 molar. And the problem with this is that um, students have a hard time rationalizing what these delta G's mean. So, for example, here's what I mean. If you calculate delta G for this reaction, water turning into gaseous water under standard conditions, 25 degrees Celsius, 1 atm, 1 molar, you find that delta G is a positive 8.59 kilojoules per mole. And at first glance, you may say, wait a minute, that doesn't make any sense. Here's what this is saying. This is saying under standard thermodynamic conditions, water will not spontaneously turn into a liquid. And that is just not true under standard, like regular conditions, but not thermodynamic conditions. Here's what I mean. At 25 degrees Celsius, which again is about the temperature in the room that I'm in right now, because it's very hot up here always. But at 25 degrees Celsius, water does spontaneously turn into steam, right? Or water vapor. It evaporates on its own. I don't have to do anything. At 25 degrees Celsius, there is enough energy for this water to go from liquid to gas phase without any outside intervention. But if you look at that delta G standard value, it says that it's not. So what's going on here? Here's what's going on. In order for this value to be valid, the partial pressure of water would have to be 1 atmosphere. Now, that's what's not comparable. I'm at 1 atmosphere pressure right now, okay, or darn close, because we're pretty close to sea level here in Lancaster. But I'm at about 1 atmosphere pressure, but it's not from just water. That's 1 atmosphere of air, right? Like the total pressure of air, which is a mixture of gases, which has a tiny, tiny amount of water vapor in it. That would so air is 1 atmosphere total, tiny amount of water vapor. It's not 1 atmosphere of just pure water vapor. Okay, if you look it up, now it varies depending on the humidity, but on average, the concentration or partial pressure of water in the air is only about 0.0050 atmospheres. Makes up a very small percent of the air that we breathe in, right? Okay. Now, if you have humidification or dehumidification or whatever, that can change. But on average, it's about 0.0050 atmospheres. So we are not at thermodynamic standard conditions. I'm at about 25 degrees Celsius, but I'm not at 1 atmosphere of water vapor. So how do we correct for our non-standard conditions? Because these standard conditions, like who is ever at 1 atmosphere of steam? Nobody's ever there. That is ridiculous. So how do we correct for that? Well, of course, we got a formula for that. Okay. Oh, hang on. Let's go back. Did I miss the formula? No, I did. My thing was covering it up. I knew the formula was somewhere. Here's the formula, folks, that we've got for this. It's you can calculate delta G under non-standard conditions. Notice that that degree sign is missing. Delta G under non-standard conditions, like right now, I'm under non-standard thermodynamic conditions, is going to be equal to delta G under standard conditions plus RT ln Q. Okay, plus RT ln Q, where is Q is the reaction quotient. So you have to write the mass action expression. Remember, pure liquids and pure solids don't go in. Okay, and we can plug the concentrations or the partial pressures in there. And then R is the universal gas constant, but it is the 8.314 R. So I'll type that out for you. It is the R equals the 8.314 joules per mole times Kelvin R. So your temperatures have to be in Kelvin. And here's the problem. because these delta G values are always in kilojoules per mole, you got to divide this by 1,000. So when we plug it in, we usually plug in 0.008314 kilojoules per mole times Kelvin. So that's what goes in for our R value. So when you're using this equation, which we're going to use here in a moment, you plug your delta G standard value in, boom. We plug R, not the 0.08206 version of R, but the 8.314 version of R. But we got to divide it by 1,000 to get it in kilojoules so that these units match the units of delta G. Temperature's got to go in Kelvin, and then we plug the reaction quotient Q in here. So if you give me a second, we will actually solve for delta G non-standard for water, and we're going to prove that water does indeed evaporate spontaneously. I know it's very riveting. You guys probably never thought, oh my goodness, tonight we're going to prove mathematically that water will evaporate at 25 degrees Celsius, but you know, surprise, surprise, here we are. Let's prove that water really does evaporate at about 25 degrees Celsius. How do we do that? Well, we're going to say our delta G under non-standard conditions equals our delta G under standard conditions, 8.59 kilojoules per mole time, kilojoules per mole, just kilojoules per mole, plus R, which is 0.008314 kilojoules per mole times Kelvin, times the temperature, which is 298 Kelvin, times the natural log of the reaction quotient. So what's the reaction quotient? Well, that's going to be Kp equals the partial pressure of water, okay, the partial pressure of water over, that's a pure liquid, so 1, it's just the partial pressure of water. Now we said the partial pressure of water typically is about 0.00500. So now all that's left to do is just plug that in. So here we go. 8.59 plus 0.008314 times 298 times the natural log of 0.005. And we get delta G non-standard is negative 4.54 kilojoules per mole, because the Kelvin cancels out. We've done it, folks. We just proved that water will indeed evaporate. It will go from liquid to gas, as if the partial pressure in here, the humidity in here is about 0.005, right? We can figure that out, okay? Because we got a negative value that tells us this is spontaneous. Let's do it. Let's solve for when at 25 degrees Celsius, what must the humidity have to be? What must the partial pressure have to be, okay? To have condensation happen, for water to not evaporate. How concentrated, how much water must have to be in the air? So how would we solve for that? Well, what we would do when the water goes from evaporating spontaneously to not evaporating, that's when delta G non-standard would equal 0. So we plug a 0 in for that. We say our delta G is 8.59 kilojoules per mole plus R 0.008314 kilojoules per mole times Kelvin. Let's stay at that same 25 degrees Celsius, 298 Kelvin, and then times the natural log of Q, which is just the partial pressure of water for this one, because it's such a simple mass action expression. So we're going to solve for Q, and Q is going to tell us essentially what the partial pressure of water has to be before water will stop evaporating and start condensing, right? That's really the dew point. Okay, so let's solve this thing. Oh my goodness, what do we got? We are going to, we are going to subtract 8.59 from both sides. So negative 8.59 equals, I'm going to multiply those two, 0.008314 times 298. That's 2.48 times the natural log of Q. I'm going to divide both sides by 2.48. Sorry if you guys can hear my dogs barking down there. That's negative 3.46 equals the natural log of Q. Then we do e to the on both sides to undo the natural log. And we find that Q equals 0.0313. So what does that mean? That means that the pressure of water, the partial pressure, the amount of water vapor in the air, the humidity, has to be 0.0313 atmospheres of pressure. If you get more than 0.0313 atmospheres of pressure at 25 degrees Celsius, if the amount of water dissolved in the air is more than that, then water will not evaporate. In fact, it will go the opposite direction. It'll be non-spontaneous in evaporation and be spontaneous in condensation. So this is an important formula. What it allows you to do is to take these sometimes silly delta G standards. No one's ever at a full atmosphere of water vapor, of steam. That's insane, right? These are silly values. It allows us to take these silly values, turn them into something far more meaningful, right? Like what am I at right now? Okay, so you could see that. What we get? 0.0313. I don't know if that graph has a value on it or not. Oh my goodness, look at that. Look at that, folks. I don't know, I can't zoom in. If you squint, 0.0313, we just solved for it, folks. We just solved for it. Okay, it's just the power signs. Okay, so when you are below that, water evaporates. When you're above that, water condenses. There's your partial pressure value. Okay. Go ahead, folks. I'll let you try this one. What is delta G non-standard under the following conditions? And let's once again be at 25 degrees Celsius. So how about that? We could pick any temperature here, but let's say at 25 degrees Celsius. I want you to try this problem. Now, this one's going to be a little more difficult. Okay, so remember the equation. Delta G equals delta G standard plus RTLNQ. Okay, remember the equation. You're going to have to write a mass action expression. Here's your Q values, the initial partial pressures. Okay, and see if you can't find it's spontaneous under standard conditions, but we're not at standard conditions because we only have 0.1 ATM of these guys and we got 2 ATM of that guy. So go ahead and give that one a shot. You got this, folks. All right, let's do this. So here we go. We got to calculate Q. So you need to write a mass action expression. That equilibrium chapter, I'm telling you, it even permeates this stuff a little bit, right? At that equilibrium, I always tell everybody, equilibrium is Chem 102. It just is. Equilibrium weasels its way into essentially everything in Chem 102 except for kinetics, right? It's just wild. It's wild how it does that. But anyway, we got to plug that stuff in here. Here we go. So the pressure of NO2, that's going to be 2 squared over 0.1 squared times 0.1, so 0.1 cubed. So what do we got here? We got 4 divided by 0.1 cubed. So Q is 4,000, folks. 4,000. That's what I got. If you got something different, please let me know. Here we go. Delta G under non-standard conditions equals delta G under standard conditions. Negative 71.2. That's kilojoules per mole. They didn't put the mole there, but we will. Plus R, 0.008314 kilojoules per mole times Kelvin, times the temperature, which is 298 Kelvin, times the natural log of 4,000. And we get negative 50.7 kilojoules per mole, folks. What does that mean? Even under these non-standard conditions, where we have way less than 1 atmosphere of partial pressure for the NO and the O2, and we have more than an atmosphere of pressure for the NO2, even under these non-standard conditions, folks, it's still spontaneous. Still spontaneous. So, yeah, it's just this formula is really what makes these delta G standard values, delta H standard values, delta S standard values, it's really what makes useful. That